by thanking Mathilde for inviting me here and also the organizers. It's a pretty amazing place, so I'm very excited. So as Mathilde has said, I'm going to talk about collective phenomena in light matter interfaces, pretty broadly define what I mean by light matter interfaces. Okay, so I decided that I should start by just saying why we care about having light matter interfaces. And so in general, this is something that basically is a requirement for doing many of the interesting things that we want to do in quantum optics and quantum information science. So for instance, if we think about quantum communications where photons transmit information, they are really good candidates for doing that, but basically because they don't interact with each other in free space. But as soon as we want to process that information, we need some light matter interface to basically make them interact with each other. If we want to realize quantum nonlinear optics, the same kind of situation occurs. We actually need some matter to create nonlinearities. So in general, bulk media are weakly nonlinear, whereas atoms, because they are at least considered to be two-level systems, they are strongly nonlinear. And so they constitute a perfect light matter interface for quantum nonlinear optics. If we want to do many-body physics with atoms that where the interactions are mediated by photons, or also if we want to study many-body physics for photons that dress atoms, we require light matter interfaces, and so on and so forth, also for metrology, sensing, imaging. Basically, everything depends on having a strong light matter coupling, and so a light matter interface. So what is the problem generally in quantum optics is the following. If we have an atom in free space, so this guy here, and we send some laser beam into it, the probability of interaction between this atom and this, for instance, Gaussian beam is very small because it's given by the ratio of the absorption cross-section of the atom that scales with the square of the wavelength of the light divided by the mode area. And because of the diffraction limit, we cannot focus the light arbitrarily into an arbitrarily small point. So then this probability is actually quite small. So that's why people have been working for decades on making interactions between light and atoms more efficient. So the first thing that one can think of doing is just having an ensemble. So it's kind of a brute force approach. You just put many atoms, and thus the interaction is going to increase. The other option is to use a cavity. So some, for instance, a nanostructure that is going to confine light and thus make the probability of interaction larger. And the other option that is also what I'm going to talk about later in my lecture of I think in the afternoon, is to combine both ideas, having many atoms close to nanostructures, and take advantage of the interactions between atoms, and thus realize more efficient light matter interactions. Okay, so maybe I should stop just for a second and say if you have any questions, feel free to interrupt me at will. Okay, so typical light matter interface are disordered ensembles of atoms. So here I have, I'm showing two references, one of the group of Robin Kaiser and the other of the group of Luis Orozco, where they have looked at collective phenomena, in particular super radiance and super and subradiance in that other case, where they send light to a disordered ensemble and they measure the light emitted, which is basically a mapping of the excitation of these atoms. And they see that first this excitation decays very fast, so it's a super radiant decay, as I will explain later today. And then eventually it stabilizes, and this is a signature of subradiance. So these are examples of collective phenomena in a very common light matter interface that is an atomic ensemble. As I've mentioned, there are other ways besides just working with ensembles of enhancing light matter interaction. The first one is to put atoms in a cavity. This is the field of cavity QED. So this has been going on for decades. And the basic idea is the following. We have the atom that previously interacted very weakly with a photon that comes from free space. now the photon is confined in this cavity, so it's going to be bouncing, and eventually this interaction is going to be increased. And if we think about how to characterize the efficiency of this interaction, one can come up with a figure of merit, that is the cooperativity. And this cooperativity is a ratio between good couplings, kind of, and bad couplings. So what is a good coupling is basically once the atom is excited and it decays into the cavity mode at a rate g. So that's good because we want the atom to mostly decay into the cavity. But decay rate is that of the cavity, that basically eventually the photon is going to escape into free space and it's going to be lost. And another kind of bad coupling is this thing that I'm calling gamma prime, that is, once the atom is excited, it can indeed decay into the cavity, and we engineer the cavity such that this decay rate is large, but it can also decay into any other mode that is not the cavity mode, into free space. So we lose the photon. So more recently, people have been thinking on other kinds of light matter interfaces, maybe a bit more sophisticated. So this has given rise of the field of waveguide QED. And so the idea is very similar. So we have an atom, and we place it close to a nanostructure, and this is, in this case, a one-dimensional photonic reservoir. So if we place it close enough, this atom is going to interact with photons that propagate through the waveguide. And again, we can talk about another figure of merit, that is the optical depth. And it's again a ratio between good coupling, the emission of the photon into the waveguide, versus emission into free space. And so once you have decided that you're going to couple an atom to, for instance, a fiber, or you're going to put it in a cavity, there is nothing much that you can do besides putting many of them. So generally, it is conventionally thought, at least, that then these figures of merit get multiplied by the number of atoms in the vicinity of the nanostructure. Yes?
So when you say it's coupled to a photon waveguide, you mean interact with the emission wave?
Yes, so when you put the atom close to a fiber, so this fiber, for instance, supports guided modes. And so these guided modes have some evanescent tail. And so you put the atom here, and it will see basically the decay rate will be enhanced by some kind of Purcell factor that is related with how close the atom is, what is for instance, the electric constant of the fiber, things like this. Did I answer your question? Okay, so I just wanted to show you some examples of what structures people have been thinking about. So here we have a cavity of the group of Jeff Kimmel at Caltech. As it's a Fabry-Perot cavity with some dielectric mirrors. People have been thinking in placing atoms in more sophisticated cavities. So this is a photonic crystal, where by tailoring a bit the structure in some given point, one can create a field localization and thus make a dielectric cavity. So this is from the group of Misha Lukin at Harvard. And these ideas of cavities and atoms are not just particular to atoms. They also can be explored in other kind of systems. So for instance, here there is a superconducting cavity from the group of Andreas Wallraff, and this works for superconducting qubits. So for instance, transmons. So it's a very different frequency regime, but the physics is similar. And there is something a bit boring about cavity QED. I'm sorry if you work in cavity QED, I apologize. What I mean what I mean is that there is something a bit trivial in the sense that what if we want to engineer interesting interactions between atoms in a cavity? It's not so easy because all the atoms talk at the same strength with the cavity mode, and so they talk to the cavity in kind of a symmetric way. So the kind of interactions that we can engineer between the atoms is very limited. Whereas in waveguide QED, we have other knobs that we can tune. So in particular, we can tune the interaction range between atoms. We can also play with the character of the interaction, so we can make them more dissipative, more coherent. We can do that by placing the atoms in specific positions, or we can also engineer the dispersion relation of the waveguides. So for instance, here, examples of what people have been doing are atoms trapped that you see here in red. They are fluorescent by the group of Julien Laura in Paris. So this is a nanofiber. they're sending light, and you see the atoms scattering the light. Again, these ideas work in other kind of domains. So these are superconducting qubits, transmons, coupled to a transmission line. So transmission line is here depicted in orange, and here you have like some small superconducting qubits. So this is some recent work from the group of Oscar Painter in Caltech. Again, the group of Jeff Kimball has been pioneering photonic crystal waveguides. So in this case, the situation is a bit different from the fiber. What you do is you modulate the refractive index, basically, of a nanostructure, and this creates a band gap for photons, where photons cannot propagate. So it's the same as basically a system that has a gap in solid state for electrons. The same thing happens for photons. And so this gives rise to interesting interactions if you put a couple of atoms and the resonance frequency of these atoms is in the band gap of this photonic crystal. And again, other kind of emitters that one can think of, not just atoms. People have been playing with color centers in diamonds. So this is some work from the group of Misha Lukin. And so these are, this is kind of an overview of the nanophotonic light matter interfaces. But there is also very interesting work from the groups of Antoine Brouwer, who is here, and also from the group of Misha Lukin at Harvard, among others, where they have come up with another kind of light matter interface that are atomic arrays, ordered atomic arrays, not disordered ensembles. So here we have a recent experiment where they saw a very well ordered 1D array of atoms. Antoine has pioneered the 2D lattices with very interesting shapes like heart here, and even 3D. And so here, because we're in France, I chose the Eiffel Tower, but he has also very beautiful other shapes. So in this case, if you think of, atoms you could trap these atoms very far away relative to the wavelength of the transition of the atoms. And then there is not going to be interference in how they interact with light. On the other hand, if you trap these atoms close enough, there is going to be interference, and this is something I'll talk about in my second lecture. And then you can start thinking in, well, there's going to be correlations in how this ensemble now talks to light. And you can think of this as now some sort of quantum nanostructure. So you could think of this as a mirror. You could think of this as a waveguide. But that is going to be intrinsically quantum, because instead of functionalizing dielectrics with atoms, that is what I've been showing you in the previous slide, where people put atoms close to the electrics. Here you can think of nanophotonic structures that are quantum by themselves, because they are made of atoms. So there is another knob that you can play with. Just for the sake of showing even more nice pictures, there are other options. You don't have to use optical tweezers. You could think of looking at how light interacts with arrays of atoms that are made by optical lattices in quantum gas microscopes. So here there is very recent work on basically very well confined atoms in an optical lattice. So this is just a preview of what I'm going to talk about in the second part of the lecture. I will focus, or in the second lecture of today, I will focus on collective phenomena that can happen in these novel light matter interfaces. So we have shown that this kind of phenomena where interference plays a role can be helpful to realize quantum information applications such as quantum memories. People have realized also that 2D arrays of atoms serve as a perfect mirror for light. So this is a 2D array reflecting light that comes in this direction. So this is work by the groups of Misha Lukin and also Charles Adams. Also, you can think of engineering some basically topological transport into the lattices. And all these things that I've been pointing to are single particle physics, where you just have one excitation. But this idea of collective phenomena is actually a many-body concept. So as I will discuss later, you can think of what happens when you have several of these excitations colliding. So it's pretty rich physics. And as I've said, this is all very universal. So most of the time when I will be talking about atoms, I just want you to be very aware that everything I say almost is compatible with superconducting systems, so transons, for instance, and solid-state emitters, also probably quantum dots, molecules. So it's very universal physics, and it all is about dipoles, whether they are quantum or classical, so some emitters interacting with light, okay? So with this, I just want to tell you a bit about my lecture. So today I'm going to talk about atom-light interactions, and I will introduce the theoretical formalism that we call the spin model. And so for my lecture 2, I think I don't have time to finish my lecture 1, so there will be a part of this that will drip into lecture 2. But then in lecture 2, I will talk about atom arrays as light matter interfaces. And in lecture 3, I will talk about atom-atom interactions in non-conventional baths, which I mean by this, for instance, atoms coupled to waveguides, to photonic crystals, and so on. And I will discuss potential applications. Okay, so with this, I'm going to start my first lecture, and then the blackboard begins. So. Okay, so I've been told that last week they told you about quantizing the field in a cavity, so James Cummings, formalism, and so on. So today what I'm going to talk about something a bit different. I'm going to talk about how to quantize the field in terms of Green's functions and how to derive a spin model for atom-atom interactions where we integrate out the photons completely, and so we only have atomic degrees of freedom. Okay, so let me begin by saying what I'm going to talk about. So I'm going to mention some basics about kind of big picture, and I will discuss how basically atoms look like. And then the second part will be about this spin model for atom-atom interactions. So first I'm going to talk about a hand-wavy way or hand-wavy quantization. I will talk about properties of Green's functions. Which are the propagators of the electromagnetic field, so it makes sense that they appear here. And then I will talk about basically a formal quantization. Okay, so then let's start by the basics. Yeah.
Should you put your notes on the website or not yet?
I can put them, but they are not right now. Yeah.
But you will, or?
Yes, if you want. I don't think I can say no now, so yes. Okay, so let's start by the basics. I think I've mentioned, I want to just discuss two important things. So I've mentioned briefly applications, but one thing I have mentioned not so much is basically emergent phenomena or out of equilibrium phenomena. Okay, so regarding, I mean, this is why I think in understanding interactions between atoms that are photomediated is interesting. First, from the perspective of applications, we have many concepts that rely on strong light matter interactions. So one can think of, as I've mentioned, like quantum communication, computing, metrology, such as, for instance, the atomic clocks, lattice atomic clocks, or super radiant laser sensing, so how to feel magnetic fields, for instance, with atoms. So all these ideas require a strong light-matter coupling, but the problem is that photons do not interact with each other in vacuum. So one requires matter, right? So basically atoms. And matter brings good things and bad things. So on the good side, it brings nonlinearity. Or interactions. On the bad part, it typically involves dissipation, which can be, well, my second lecture will be about how one can make use of this dissipation to do interesting things, but it's typically considered to be detrimental. And so one thing I mentioned briefly in my slides is that atoms are very nonlinear. Basically due to Coulomb potential. So if we have an atom, the most toy model atom possible is ground state and an excited state that are separated by some energy, omega 0. And so this could be, for instance, the ground state. We have one electron in a 1s orbital, and the excited state can be, for instance, a 2p orbital. And so this is in energy. Is this picture? And so if we come with a photon that is resonant to this difference in energy, if we move the population from the ground state to the excited state, if we send another photon, it will not be resonant with other atomic levels. So basically this means that this atom interacts very differently with one photon than with two photons than with three photons. So it's very nonlinear. It's very different from the typical, bulk media. And so the second thing that I want to say is that if we have an atom in the excited state, once it is in the excited state, it's always surrounded by a bath, that is the bath of all the electromagnetic field, all the field modes, and this leads to decay. So there's going to be an emission of a photon, and now the atom is going to decay back to the ground state. Okay, so once we think of an atom interacting with a lot of field modes, you think of it as basically an atom coupled to a dissipative system, to a bath, and this leads to decay. Okay, so now I'm going to mention some typical energy scales. So for the frequency, the resonant frequency of the atom, we have omega 0 is of the order of, for instance, 300 terahertz. So this is, of course, atom dependent, but for alkalis like rubidium, cesium, and so on, that seems to be a reasonable, and again for specific transitions, but this seems to be a reasonable frequency that you can encounter. And there is also line width that is basically associated with the decay rate from the excited state, how long your excitation is going to live. And so this line width is of the order of tens of megahertz. Again, this depends on the specific transition. So for instance, there are clock transitions where the decay rate is much smaller and the excitation lives for much longer times. So again, it's very atom specific. And so one can define the Q factor as omega 0 divided by gamma 0, and this tends to be of the order of 10 to the 7, 10 to the 8. Again, it depends on the specific line width and transition. And this means that they are, these atoms are high Q. You can think of them as high Q resonators. So for the resonance frequency, the line width is typically very narrow. And another thing that one can, another energy scale is that of temperature. So at 300 Kelvin, KBT is much smaller than h bar omega 0. So basically, there is no thermal excitation of the excited state. So if you have an atom and you're not sending light to this atom, it's typically in a ground state. It's not going to be thermally excited. This is, for instance, different from the case of superconducting qubits. So in this case, the resonance frequency is of the order of gigahertz, and that's why you have to do experiments in dilution bridges to prevent this. Okay. So now let me tell you a bit about how atoms interact with light, very briefly. So if we have, again, we have our picture of a two-level atom, ground state and excited state, and we send a photon. This photon is going to induce a dipole moment in my atom. So basically, light induces a dipole moment. In the atom. And so now I can describe my atom as a point particle because it's tiny compared to the wavelength of the photon. It has a dipole moment that is proportional to two things. I'm not going to be very formal now. I'll be more formal later. I just want to mention two things that are important. So I have basically a transition matrix element. So this tells me about the strength of this transition. And it's specific to basically the orbitals that are involved in the transition. So it's something that looks like this, ERE. So it's this matrix element of the position operator between the excited and the ground states. And so it depends on the properties of the wave functions of the ground and excited states. And it also depends on things like selection rules. So depending on the parity of the specific levels involved, this could be 0. This transition could be forbidden, for instance. And then there is another part here that is the atomic coherence operator. That is simply this operator. So it takes the atom from the ground state and puts it in the excited state. And so, again, an atom that is just in the ground state and is not being illuminated, there is no dipole moment. An atom that is fully inverted in the excited state, there is no dipole moment. So you always have to create some coherence between the ground and excited state. And you do that by sending light. And one thing that I have been saying for some minutes is that these atoms are two-level systems, but this is typically a lie. So I've been lying to you for some time, sorry. Typically, atoms have hyperfine structure, so are multi-level systems. So hyperfine structure comes from the combination of different angular momenta. And this leads to a structure that looks potentially like this. It could have more ground states, more excited states. So this is, for instance, this number f is a number associated with hyperfine structure. So this is fg1/2, which means that the projection along the z direction for this specific quantum number leads to two states with a -1/2 and 1/2 projection, Zeeman number, mg. And we can do something similar for the excited state. For the specific atom is 3/2, and then we have me equals -3/2, -1/2, 1/2, 3/2. And so, again, this is for a specific transition that I just chose. You could have many Zeeman levels. And then, depending on basically the levels that you are interested in, they are connected by different polarizations. Such as, for instance, this level can only decay into this one and is coupled through a transition that has a polarization sigma plus, so it's circularly polarized. The same happens with this transition, so it's sigma plus. But this level can also decay into this other ground state with a polarization pi, so it's polarized along C and it's linear. So this is, in this case, we're going to have selection rules that are enforced by Clebsch-Gordan coefficients. But again, this is very complicated, and one could think that if you apply a magnetic field, these levels are sensitive to the magnetic field, so the energies between the different Zeeman levels can be split, and so this eventually may become a two-level system again. So for, I think, all of the things that I'm going to talk about today, at least, we're going to consider that atoms are two-level systems, and we're going to forget about the hyperfine complexity. Because if not, the whole thing, you can do the same that I'm going to do about deriving a spin model for the atom interaction, but it's very messy, although it can be done. Okay, so with this, I'm just going to write the simplifications and assumptions before I start with the math. So as I've said, we will consider two-level systems. So, or assume that atoms are two-level systems. All the atoms are going to be identical. So basically, they have all the same resonance frequency and line width. And our goal for today is to describe photon-mediated interactions between atoms that are in complex dielectric environment. Okay, so what do I mean by the last sentence is that my goal is to give you a formalism that is very general. So it should work for an atom that is in a cavity, should work for an atom close to a fiber, to a photonic crystal, to this table, to whatever, to many atoms. So the most general idea that I can think of. And that should work for situations that are non-trivial. So for instance, in a cavity, one doesn't have to use, for instance, the Green's function. That is something I will introduce in a bit, because it's very obvious that you have a mode, and you can find a kind of neat expression for a field mode, and you don't have to go through all the mess of dealing with Green's function. But if you are in a situation where this is not so trivial, such as, for instance, there are many field modes or the expressions are very complicated, etc., etc., at least my belief is that by quantizing using the Green's function, you simplify the problem, because you have now a formalism that you don't have to start writing always the Hamiltonian for the photons, the Hamiltonian for the atoms, the interaction, tracing them out. You skip all these, and you just write everything in terms of Green's functions. Okay, so now just as a comment related with the beginning, that I said that I think there are two interesting things. One are applications, and the other are out of equilibrium physics. I want to mention a bit about that and why this problem is a bit complicated. So when we have a collection of atoms, we're going to have emergent phenomena. That is out of equilibrium. So imagine that we have a bunch of atoms, and so I'm going to send light to them, so I'm going to drive them, and they are going to, see the environment, so they are going to decay. So it's a very out of equilibrium situation. And if the distance between the atoms is much smaller than the associated wavelength to the transition or atomic transition, then there is a very famous work by Dickey in 1954 that told us that atoms radiate collectively. And so there are physics associated with this collective radiation, and in particular we have phenomena that is called superradiance, where basically the atoms are going to decay at a rate that is much faster than a single atom would. But we also have subradiance and everything in between. So subradiance is the opposite scenario, where you have an ensemble of atoms, and because of these interactions and the interference in how they relate with the light, if you put the excitation in a subradiant state, it will stay there forever. It won't decay. And so one thing that, in the case of Dickey's problem, he assumed that the atoms are in this condition, so the distance between them is very small. So you can consider all of them being in the same spatial location. Or you can consider that they are all interact with the same field mode, so they are in a cavity. So it's a highly symmetric problem. And so this is why he could basically solve for all the states analytically. But this is not the case if you have a situation such as, for instance, what Antoine's array may show. So for instance, something like this, where the distance between the atoms is of the order of lambda 0, but you cannot think of all of them interacting, of all of them being at the same spatial location. So this is an extended array. This is a much less symmetric situation than that of Dickey. And so in this case, the problem is complicated. So imagine you want to understand the dynamics of this system, or you want to understand whether there is superradiance or subradiance, and the scaling of subradiant states with atom number, etc., then it's not trivial because there is not so much symmetry. First, we have a Hilbert space of dimension 2 to the n, because if I have n atoms. So that, of course, adds a lot of complexity. But then, on top of that, I have another set of infinite number of photon modes. Because if I want to describe my system completely, I cannot only just talk about the atoms, I also have to talk about the photons. And so the photons, there are infinite number of modes, and it's a mess. But what I'm going to claim is that in this situation, we can integrate out the photons. And we can reduce complexity. So we still have an exponentially large Hilbert space, but at least we don't have photons that are messing with us. And we can do that in specific settings. So in general, you cannot say that you can always integrate out the photonic degrees of freedom, and we will discuss when this is possible. So the idea is that what I want to end up doing in this lecture is to come up with a framework that just describes the atomic degrees of freedom of a chain or of an array of atoms, order, disorder, I don't care, in any kind of complex dielectric situation. Okay? And so, any questions? Because now I'm going to start with some math. Yes? Because all the atoms are basically in the same point. So if you think of this situation, if I write I will talk about this in a moment, but if I think of how the propagator of the field looks between these two atoms, this is the Green's function, between atom I and atom J, I have something that looks like e to the I k Ri minus Rj. Here I have something that is Ri minus Rj cubed, and here I have a lot of things. I will tell you about this later, but the problem is that this atom talks to this atom at let's say, at a given rate. But with this atom, it's different, and with this atom, it's different. Whereas in the case of the key, or if you think of all the atoms being in the same position, or in a cavity where basically the interaction range is infinite, there is all the atoms, this atom would talk to this at the same rate as with this, and at the same rate as with this. So the complexity is lower. Any other question? No? Okay. So now let's talk about this spin model. Okay, so now let's imagine that we have atoms in some complicated, or close to some complicated nanostructure. So here I'm depicting one of Jeff Kimball's photonic crystals. And so he's able to trap the atoms close to the gap. And they are not in, they are kind of flying around, so they are not so ordered as in my picture. And so what is the traditional approach that you would follow in this situation is to write a normal mode decomposition for the field modes of this nanostructure and write the Hamiltonian. So I'm going to write a Hamiltonian that is the free Hamiltonian and the atom field interaction Hamiltonian. And so H0 is a Hamiltonian that describes the atoms, but also the field. And so the Hamiltonian for the atoms is just the sum from j equals 1 to n. Imagine that I have n atoms of the energy of these atoms, where this is an operator that is this. So if the atom is excited, I count it basically. And then I have the Hamiltonian for the field. And this is the traditional approach. It's a sum of all case polarizations, which I'm denoting as what? Mu. So this is the polarization, for instance, of the energy of the normal mode times some bosonic operator, A plus K mu, AK mu. So here what I'm intrinsically doing is basically I'm finding a normal mode decomposition. Of the field. And I'm associating some bosonic mode. Or bosonic operator. A creation and annihilation bosonic operator. Yes? In practice, so I'll talk about this in between, I think probably tomorrow. So I'll show you some videos. But so the idea, I mean, I can tell you possibilities and then what they did in the experiment. So one possibility could be maybe putting basically optical tweezers close to the, so with an optical tweezer, you have basically a dipole force that traps the atom in the position of maximum or minimum intensity, depending on the tuning between the resonance frequency of the atom and the laser frequency. And so basically this moves the atom to the position that you want. And then the complication, I mean, this is already complicated, but as I've shown you, people around the world has managed to do this, right? So that's how they have created these beautiful arrays. The complication in this case is to place it close to a nanostructure. So then if you put this light beam close to a nanostructure, it's going to distort all the, there is a lot of near field components and reflection from the nanostructure, so it may distort your trapping potential. So that's complicated. In the experiment, they didn't use optical tweezers. So what they did, and also that's why they didn't trap basically in any order fashion. So what they did is they created a mod, and they transferred the atoms to a kind of a cigar-shaped trap that is, so just for the sake of dimensions, this is like 370 nanometers, I think. This is around 200 nanometers. And this has some thickness also around 200 nanometers. And so this is in a vacuum chamber, and it's floating. Okay, it's a very long nanostructure that is floating. As you can imagine, that's very hard. Like any kind of vibration can destroy it, or if you heat it because it's in vacuum, it can only radiate the heat, so it can melt. So there are many challenges associated with this experiment. But they managed to do this nanostructure. They managed to put in the vacuum chamber, and then what they trap the atoms in a cigar-shaped trap that is also at, I don't know, other maybe 200 nanometers away. So I might be a bit wrong with the numbers, but I can give you a reference and you can double check. And so the atoms are confined in this direction, but so they will be not very far away, but they can move freely around here. So they are not trapped in this direction. So it's not the situation where I told you here that they are in any kind of order situation. But you can think that you could trap them if basically this photonic crystal, because of this periodicity, it has some block mode. So the field is not uniform like in a fiber. It has periodicity. So it has regions of high intensity and low intensity. So you could use that to trap in an ordered fashion. But this hasn't been done in practice yet. So this I'll talk about it, I think, in the last class when I talk about nanophotonic structures. Okay, so any other questions? I mean, and this is generic. I mean, I just chose this system because in this particular case, it's not easy to do this because you have to find the normal mode decomposition of a structure that is very complicated. So how do you do that? But again, I could have drawn a cavity, but then in a cavity you would say, why do you want me to go through this pain that I'm gonna put you through? If I know that it's a cavity, then what's the point? Yeah. So I just wanted to draw something a bit more scary. Okay. So as I was mentioning, this strategy is fine if you basically know if there are, for instance, few modes that are relevant. For instance, if you have a high Q cavity. But it's a bit harder if you have creatures like that one. So you have to resort to something different. And we want something more general. So again, like usually what you do is you write this Hamiltonian, and then you want to integrate out the photonic degrees of freedom. So you have to be messing around with the dispersion relation, and it's very complicated. So what I want to do is to end up in a basically a Hamiltonian that just keeps track of the spin degrees of freedom, the atomic degrees of freedom, and where you can decouple the electromagnetic problem from the quantum mechanical problem. Okay, so that's we will do that using the Green's function. Okay, so I'm gonna erase this. So what I'm gonna look for is a more general approach. Using Green's functions or electromagnetic Green's functions. And the idea is you basically solve the electromagnetic problem first and integrate out the photons basically, and then you do quantum mechanics. Okay? And so, as I've mentioned before, it is not always possible to integrate out the photonic degrees of freedom. So what do I mean by integrating out photonic degrees of freedom? I have my atoms. And in general, if I have atoms interacting with photons, I can describe this system by a Hamiltonian. It is, the evolution is unitary. There is no dissipation. I'm keeping track of everything. However, I can think of, well, I'm going to have my system of atoms that are coupled to a bath, which are the photons. So this is the idea of tracing out. So now my electromagnetic degrees of freedom are just a bath for the atom. So this is like what you do in statistical mechanics. You have now a reservoir. And in this case, when you trace out the photonic degrees of freedom, this leads to dissipation. And decay. So what do I mean by this? If I have an atom and it emits a photon, and I keep track of this photon. So again, the dynamics is Hamiltonian, is unitary. There is no decay. So the atom goes to the ground state, but I have a photon. energy is conserved. However, when I don't keep track of the photon that has been emitted, because the atom now is interacting with many photonic degrees of freedom, in that case, this leads to the picture of I have an atom in the excited state, it goes to the ground state, and this energy has been lost. So there is decay in the problem. And this happens whenever I trace out degrees of freedom. So what do I win by this? Well, I have introduced dissipation in my problem, but I have also reduced the complexity because I don't have to keep track of all these many degrees of freedom. So you lose some, you win some. Okay. So is this clear? Any questions? No. Okay, so now what I'm going to do is, before I tell you how to actually quantize the field using Green's functions, what I'm going to do is a hand-wavy approach on what one has to do. So what I'm going to do is forget about quantum mechanics for some minutes. I'm going to think of atoms as being classical dipoles. I'm going to tell you how classical dipoles interact with each other. I'm going to introduce the Green's function. And from there, in a very, very hand-wavy fashion, I'm going to find a Hamiltonian. And then I'll do the quantum version of that, which is more complicated. And you'll see that, more or less, we guessed kind of right the first time. Okay. And this will also help me because then I can introduce Green's functions from in a classical setting. So I'm going to do the hand-wavy quantization. So please don't ever quote me on this. This is like, by all means, is wrong. It's just a way of just giving you an intuition, okay? And then we'll do the right version. So the idea is that we're going to quantize classical dipoles. So again, atoms are dipoles, so it just happens that they are quantum, so that's the complexity. So imagine that I have a bunch of dipoles in some dielectric medium. So I have n dipoles, and I'm driving them with some external field. Okay. And each dipole I characterize by dipole moment that is at a given position. For dipole j, it's at rj, and well, it oscillates in time. And I'm going to consider, for the sake of simplicity, that I have a monochromatic field. So the driving field is monochromatic, and then all the fields that are generated in the problem are monochromatic. And so I'm going to write this as E plus R omega e to the minus I omega t plus E minus R omega e to the I omega t. And because this, I might change notation, this is just E of R omega, and this is E asterisk of R omega, the complex conjugate. Okay? So what I'm going to tell you is basically now in Jackson textbook, so nothing very sophisticated. And the idea is, what we want to find out is to write the Hamiltonian of this bunch of dipoles and to write the expression for the field in any point in a space generated by this ensemble of dipoles, okay, that are being driven. So what do we have to do? We just have to write Maxwell's equations. And I'm going to write them in the frequency domain, and I'm going to assume that the medium is not magnetic. So I have the following equations of R omega is I omega B of R omega. I have the curl of this of R omega minus I omega epsilon 0 epsilon of R omega E of R omega plus a current. And then I have the divergence. And I have and this is some charge density, and this is some current density, and the only thing that I'm saying is this kind of environment, I describe it by a permittivity that depends on the position, because why not? Okay, so far I haven't done anything. I just wrote the Maxwell's equation, so there is nothing fancy. But then I'm gonna write for you the wave equation. So I'm gonna combine these two first equations. I'm gonna find the wave equation for the electromagnetic field, whose fundamental solution is the Green's function. And then I will discuss why this is useful.
So what is the small e?
The small e is the permittivity of the medium, the dielectric permittivity. Okay, so if we combine 1 and 2, where 1 and 2 are the first two equations, then we get the wave equation, which is this. All this is acting on the electric field. And the source is a current. And this is the wave equation for E. There will be another for the magnetic field. So what this tells me is that if I have a current in my medium, it's going to generate a field according to this wave equation. Okay? And so what I can do is I can go and try to solve this equation. And the way of solving this equation in an elegant manner is to invoke the Green's function. So we solve the equation introducing the Green's function. Whoa. Which is, you say that you have this same equation. But now this differential operator acts on the Green's function, which is a tensor. So I have added this thing here. So I will forget this all the time, but just keep on mind that this is a tensor, and I will explain why this is the case. And this has now two spatial components, R and R prime. And now this equation looks like this. So how is this a solution of the previous equation? So this equation is the Green's function is the fundamental solution of the wave equation, because it is the solution where the source is a delta function. Okay? So instead of any kind of complicated current, is the source when we have a point in homogeneity. Okay? And the beauty of the Green's function is that once you find it, you can find the field generated by any distribution of current. And why is this the case? It's, well, I have to put another condition also. That is that G of R, R prime omega goes to 0 when R minus R prime goes to infinity. So basically that the field basically decays. And the beauty of Green's functions, and again, this is not just the electromagnetic Green's function, is any Green's function is by definition this, is that if I now want to write the field generated by any current, this is this, I mu 0 omega integral in r prime of gr r prime omega dot product g of r prime omega. And you can check that this equation is a solution by plugging the field in the wave equation, and you will end up with this. So it's some sort of mathematical manipulation, but it's very elegant because it just says that once you have found the Green's function, you have solved the electromagnetic problem. And so the electromagnetic problem is given by, for instance, the boundary conditions. You can have, a fiber or a photonic crystal or something very complicated. Then imagine that you don't know about Green's function, and you say, well, I want to calculate the field here, generated by a current here. So I have to solve the problem once. And now what if I change the current to be here and be different? Then I have to solve the problem again. And then what if I change the current? Then I have to solve the problem again. So it's a mess. But the beauty of the Green's function is that you just solve the problem with a point in homogeneity. And then once you have found the Green's function, you can find the field generated in any point in space by any arbitrary current. So you have solved it, basically. Of course, there is a problem that is not so easy to find the Green's function. If not, our life will be very easy. But we will deal with that in a minute. Okay. So, because basically we can calculate the field in any point that is produced by the current, the Green's function is the propagator of the field. And so again, once you have the propagator of your problem, you have solved the problem. And also, in the case that we were thinking about, that is the ensemble of dipoles, this is even simpler, because now our current is going to be generated by a point dipole. And so the current looks something like this. So imagine that we have dipole at R0, and it's a point. Well, this generates a current that looks like this. And then if we put this thing here, and we integrate in volume, then we get a very simple expression for the field. E of r omega is mu 0 omega squared times g r prime omega dot p at r omega, and here I have r0, and here I have r0. This is a tensor. So it's a very simple expression. And again, so what this means is the following. If I have a dipole at position R0, I want to calculate the field at any position. I just have to multiply this dipole by the Green's function. And because electromagnetism is a vectorial theory, a dipole that is polarized along x can generate a field that is along x, but also along y, also along c. So that's why the Green's function is a tensor. And so G I is something that depends on polarization indices. Okay, so it's alpha, beta, could be x, y, or z, for instance, in Cartesian components. And so this would be, for instance, if I have a dipole pointing along x, the field along x will be the xx component of the Green's function, the field along y will be the yx, the field along c will be the cx. Okay? Okay, we're getting close. And so we didn't have just one dipole, we had a collection of dipoles. So then we can generalize this expression and make a sum. So if we have a collection of driven dipoles, the total field in any point in space is going to be the driving field plus the scatter field, which is this field generated by the dipoles. So this is the drive, and this is the scattering. Okay, so now we know the field in any point in space, and so we are very close to being done with the classical treatment. Any questions so far?
What is that expression just come from?
Oh, so it's just, imagine that you have many of them, so the same as before, and we're driving them with a given external field. So I have a sum from J equals 1 to n. And so we know that for a given dipole, just one, the field is just the Green's function times dipole. So now if I have a collection of them, I have to sum. So because the field is linear, right? So when you have, if you want to calculate the field radiated by two sources, you just add them, right? You don't multiply them. So you have to add the scattering by each of them. So this is going to radiate, this is going to radiate, this is going to radiate, and you want to calculate it here. So you add all of these three, but then you also, of course, have to add the free term.
Okay, so over there from the Green's function in the first line was like still a function that you integrate over, and then for the dipole it's
Here,
already a tensor.
yes.
Okay,
So for the Green's function is always a tensor, but the only thing that I'm saying is that this is generic. It's like, what is the field created by some distribution of current? And the question is, what if now this current is created by a point dipole? Okay, so it's this current is generated by a point dipole, and so then the field looks like this. Okay, so then, just so that you're acquainted with Green's functions, because we're going to use them in all lectures, I can talk about very fast, just write the properties. So the first property is related with causality, the fact that the electromagnetic field is real. So G conjugate is G at R prime minus omega. Okay? So this is related with causality. So the Green's function is a response function. So it typically, this response function typically fulfill these conditions. There is another relation, that is that G of R prime omega is the transpose when I change the spatial indices. Okay, so again, I have polarization indices in my Green's function. If I change the spatial positions between the 2 points, okay, I have to transpose. And this is related with reciprocity. So either Onsager's or Lorentz reciprocity. And this is related with, if I have a source here, this generates a field that I measured here. And the magnitude of the field is 2 in units of field. What if I now do this? Now my source is here. What is the field here? It has to be the same if the medium where the field propagates is reciprocal. So this is the case. There are mediums that are non-reciprocal, such as, for instance, magnetic mediums where you break time reversal. So in this case, this condition doesn't hold. But this condition it's used, I don't know if I will explain exactly where, it's used in our derivation. So reciprocity is an important condition. And then there is another property that I'm going to write, but just because it's kind of complicated. But again, if I put my notes, you may want to take a look at this. So this is the imaginary part of E of S omega G alpha beta R S omega G beta gamma conjugate S R prime omega, and all this is the imaginary part of G alpha gamma R prime omega. Okay, so this is another condition that is very complicated. It's just involving an integral over volume of this common spatial index of the Green's function, and also the Green's functions are contracted in beta, so this is like Einstein convention. And so when you do this integral, you find that this is the imaginary part of this other Green's function. So this is very technical, but if you want to follow the derivation that I'll do later, I won't do it, but I will tell you you need this. Okay, so I just wanted to write it. Okay. So then we're almost there. So one comment I wanted to say is that Green's functions in general are not easy to calculate. So in vacuum, it is trivial. So in vacuum, the permittivity doesn't depend on the position. The boundary conditions are trivial. So you can solve this exactly, and it's one line, it's one equation. Then in situations where there is a high symmetry, it is also possible to find the Green's function. For instance, in a half space, so infinite half space, you put the dipole in close to a half space and you can find the Green's function. It involves horrible integrals in the complex domain, and actually they were called Sommerfeld integrals, and they were doing them wrong for 50 years. So it's not trivial, but it can be done with a lot of patience. Another example is an infinite fiber of circular cross-section. Again, it involves integrals, and they are bad, but semi-analytically you can find the solution. And I guess if you have also a sphere and you put a dipole here and you want to calculate the Green's function, that's also a possibility. So situations where you have high symmetry, they are not trivial but can be done, but generically it's almost impossible to calculate it analytically. So what you have to do is you have to use some solver of Maxwell's equation. So for instance, in the nanostructure that I mentioned before, this alligator photonic crystal, you can calculate the Green's function using FTDT, so some software called numerical, where you put a dipole, you look at how you excite it, you see how it decays, and from there you can get the Green's function. So there is always a way of getting it, just not analytically. Okay, and so now I'm gonna almost end. So now we can write a hand-wavy Hamiltonian. So the Hamiltonian of my system of dipoles coupled to the field is something where I sum over all the dipoles, and this is the typical dipolar Hamiltonian. So dipole times field, right? And then I'm gonna say, okay, and this is where it gets super hand-wavy. So again, I'm not gonna say that this is formally right by any means, but the end, it looks like okay. So then I take this expression here for the field, and I'm gonna plug it there. So this becomes sum in J of P dot Pj Ej, just to make it shorter the notation. This part here, that is the driving term. So this is like, looks like a Rabi frequency. I don't know if to you, to me at least, yes. And there is another term that I take from here, mu0 omega squared. And now I have two sums. So I have a sum in I, a sum in J. Okay, because I have the sum of all the dipoles, but then this field at Rj is generated by all the other dipoles. Okay, so I have a double sum. And so I have something that looks like Prj dot product Green's function between Rj and Ri dot Pri. Okay? And then now the magic happens where things get even more hand wavy. I said that when I can quantize this dipole, and this is related with the transition matrix element times a coherence operator. Okay? So I'm going to just write this there. And then my Hamiltonian, the interaction part, just this part, not the driving term, just the part that tells me about interaction, is something that is sum ij with a mu0 and an omega 0 square p asterisk dot Green's function Ri Rj omega 0 p, and then I have the atomic coherence operators I j. Yeah. Okay, so I've done a lot of things. So first here I have written things in terms of frequency omega, some given frequency. Here, to pass from here to there, I have performed Markov's approximation, which I will do in a slow manner later when I do it in a quantized form. So now everything is evaluated at the atomic resonance frequency. I have a conjugate here because this is in time, and I have passed to frequency, and then I have converted to time again, so I have extra things. And so here I have omega 0 squared. But what I just want to tell you is that this Hamiltonian, it looks as the following. I have an atom I and an atom J. And when atom J goes from the excited to the ground state through this operator, it emits a photon that takes atom I from the ground to the excited state. Okay? So it's a flip-flop Hamiltonian. It's also a non-Hermitian Hamiltonian. So the Green's function here is not just a real number, it's complex. So this means that this Hamiltonian, if we try to evolve some state wave function with this Hamiltonian, the norm is not being conserved. Why this is non-Hermitian is because there is dissipation. So if you think of just an atom you just look at I equals J, you will have a term that just tells you about this decay. Okay, so this will factor into something that is proportional to the decay rate of a single atom. And so this is a kind of very hand-wavy way of quantizing the Hamiltonian. We can also quantize the electromagnetic field, and I'm going to do it just here. Which is the typical protocol of putting hats into things. So now this becomes E of R. The positive frequency component is the external with a hat plus the scattering term, which I am now going to change to something that has the atomic coherence operator. So there you go, quantized, super easy. I just put hats. Okay, so then of course you don't do this like this, because then who knows if you're missing something. You have to do it right. So in the following lecture, I'm going to do the quantum version of this quantization, and then I'm going to apply all this to atomic arrays. But the interesting thing is that, let me just remind you very fast, we have integrated out the photonic degrees of freedom. There is no A here, we just have spin degrees of freedom. And we have something that this Hamiltonian, I can take it, and I can say I'm going to try to solve the situation of 25 atoms in a cavity. Oh, what is the Green's function of the cavity? Oh, it's that. Okay, I can plug it here. Or now in a fiber, oh, I can plug it here. So we have decoupled the complexity from the electromagnetic part and the complexity from the quantum mechanical part. So that's why it's beautiful. And so with this, I think I'm done. And if you have questions, you can ask me, I guess.
That part a bit too quick. Why you got commuting conjugate for the RG type, but you didn't have that for the RI?
Oh, because, I mean, all this, as I've said, is very hand-wavy. So it's not, this is evaluated first in time. You have to move to frequency. You have to Markov's approximation. So here you have to play with complex conjugates. I just didn't do it. But I'll do it later when I do it right. This was just to get you familiar with Green's functions and effective Hamiltonians. Yes.
The external field in that professor.
Yes.
So it's just external field because you assume that there is no absorption by the atom?
This is just a driving field, yes. So it's, okay, so imagine that you have, the atoms are just now sources that are in some dielectric medium. And in this dielectric medium, on top of this atom, there is an external field that propagates, and it could be, you know, whatever you send. You could think of what if now I make now a kind of more generalized medium that also puts the atoms in it, you know? So I think of, I don't know if this is the question that you're asking me, but when I have a fiber and I have atoms, what I'm saying here is that the field at some point far away is the external field that comes plus the re-scattering. Okay? But I could say, what if now, and my medium is just the fiber. Okay? I could just make a black box and say, what if now I think of my medium being that, and it includes the atoms, then the Green's function that I put here will not be just the Green's function of the fiber. I'll have to modify the Green's function to account for the atoms. So you could try to do that. Eventually it's going to break down because the atoms are going to add nonlinearity, so it won't be right. But
So your Green function also counts for some dissipation of the initial electric field?
yeah, so the Green's function is given by the boundary conditions. So for instance, the dielectric constant. So if you have an absorbing medium, then yes, it will have, when light propagates and it's absorbed by the fiber, then this will show up in the Green's function.
Okay.
Yes. It accounts for loss in the medium, yes. And this is also why it's beautiful, because it's a way of quantizing in the presence of absorption.